Alright, welcome back, and we're continuing to manipulate this equation, understanding that what we actually have is a polynomial of power 2 that we're trying to solve. Eventually we'll use the quadratic formula. Again, if you're overwhelmed by the number of variables that we have, remember that the only variable we actually have is our unknown v1 final. And the rest are actually knowns. They're the masses and the initial velocities are all given. So we could plug in those numbers now if we like, and you can if you'd like. I'm not going to do that because that would introduce rounding error. Okay, so we're going to continue to manipulate this. The first thing that I've done here is I've moved this term over to the left and just pulled out the v1 final squared. Now I'm going to move the second v1 final term over. So I'll have negative 2 m1 v1 initial v1 final, and then I need to move the rest of this stuff over, and these two terms could be combined to be m2 and m1 and the quantity times v1 initial. So I'm going to do that. I'm going to move them over, and let's put m1 first, since when that goes over it'll be plus. So we'll have plus m1, and then this will be minus m2 times v1 initial squared. Now we've moved everything over to the left, so that's equal to 0. Now we're ready to solve our polynomial. So we can think of this as, this is a, this here is x squared minus, this is b, here's x again, since that's our only unknown, plus, and then all of this is c equals 0. So this is a polynomial that we can solve using the quadratic formula. So remembering the quadratic formula, we'll have the x, which is v1 final, is equal to the opposite of b, so it's going to be 2m1 v1 initial plus or minus the square root of the quantity b squared, so that's going to be 4 m1 squared v1 initial squared minus 4ac, so we'll have 4 times a m1 plus m2 times c, which is m1 minus m2, all divided by 2 times a. Now we need to do a little bit of manipulation. We look quickly at the discriminant of that radical. We can see that that's actually going to simplify really nicely. So we'll start there. This is the product that of two binomials that results in a difference of squares. So we'll have m1 squared minus m2 squared times, oh, I dropped a term here, this should be v1 initial squared. That was from C. I forgot to include that, so I'm just going to put that back in. There we go. So now we can simplify the discriminant a little bit further. So we're going to have 4m1 squared v1 initial squared minus 4m1 squared v1 initial squared plus, so I'm just sort of distributing everything into that binomial term here. So we'll get plus 4m2 squared v1 initial squared. So these two terms cancel out, and the only term left is all squares, so it's going to be easy to take the square root of. So we're going to have 2m1 v1 initial plus or minus. When we take the square root of this last remaining term here, we're going to get 2m2 v1 initial all divided by 2m1 plus m2. So all the 2's are going to cancel out, and we're going to be left with our expression, which is m1 plus or minus m2 over m1 plus m2 equals v1 initial. Now the quadratic formula gave us two answers resulting from this plus or minus sign. One of those answers is not physically relevant for this situation. If the answer provided by adding mass 1 and mass 2 gives this ratio a value of 1, which means that the value of the velocity for the first object is unchanged during the collision, and that doesn't make physical sense in this case. So that solution is thrown out, and the only solution that makes physical sense is the other one. So this is our answer. And we can see that the final velocity after the collision is actually related to the ratio provided by the two masses and the initial velocity. We can find velocity final 2 by remembering that we had an equation for it that was related to v1 initial and v1 final. And we'll have to substitute. So what we're going to do is we're going to take our new result, we're going to substitute it in there, and then we'll get an expression for v2 final in terms of the ratio of masses and v1 initial. And again, it's going to take a little bit of algebraic manipulation to get the answer. So I'm going to show you the steps. The book also doesn't show you how to do this step either. So all I've done so far is replaced v1 final with the expression we just found. We're going to want to put those two terms together as a single fraction. So I'm going to multiply the first term by m1 plus m2 over m1 plus m2. That way I can combine the two fractions with each other. And combining those numerators, we're going to get m1 plus m2 minus m1 plus m2 over m1 plus m2 times v1 initial. So here both terms had v1 initial, so I factored that out. And then again, this negative sign got distributed, so we had a negative m1 and a positive m2. Now everything is in the numerator. The two m1s are going to cancel out. We're going to get 2m2. So this is going to start to simplify, look a bit nicer. We'll have 2m2 over m1 plus m2 v1 initial. And then we can finally cancel out with the fraction that was sitting out front. And we'll get v2 final is equal to 2 m1 divided by m1 plus m2 v1 initial, and that's our second equation. So again, you can see that the final velocity of the second particle after the collision is related to some ratio of the masses and the velocity of the particle that was moving before the collision. At this point, we can take the values that we were given and plug them into the two equations that we found to find the two unknowns, the velocities of the two particles after the collision. So in case you were wondering, these two equations that we found would be true only for this situation. And this situation is an elastic head-on collision. An elastic meaning that the energy and the momentum are conserved. And only for a situation where one of the particles is moving and one is at rest. So this is a very specific situation. Not really an equation for you to memorize. It's really the steps in the process that are important.